Everyone. We've got a few more folks joining us from the waiting room. We'll just take a second while they're transitioning in. Welcome to this month's session, AI and Bioimaging Community Discussion. These are been terrifically successful programs for well over the last year. For those I don't know, my name is Ken Shopman. I'm ABRF's Executive Director. I'm just going to go over a few housekeeping notes and some reminders, and then we will turn it over to our terrific presenters for today. Let me just get set to share the screen here. Hold on. All right, now. Okay. Terrific. Hopefully you are seeing our slide here. Just a couple of updates. Feel free to introduce yourself in the chat, where you're connecting from, your institution, your location. Post the questions in the chat. Presenters will cover those following their conversations. And then if you have suggestions for future programs, whether it's in this series or other topics that you'd like to see ABRF present, please share those, send those to us. We're happy to fill out the calendar, and we'll go over some of those upcoming programs in a second. Speaking of ABRF updates, I'm sure everyone is familiar with ABRF's brand new updated strategy. These are the 4 goals we'll be pursuing over the next close to 3 years. If you'd like to contribute, each of these groups has a task force. Some of our presenters are involved in those as well. If you'd have ideas and would like to contribute, again, feel free to reach out to us. We'd be happy to have your help and support in making progress towards these 4 goals. Looking at it differently, these are some of the objectives and activities that the task forces are pursuing along the lines of those goals. All right, some other activities that'll be happening in ABRF over the next couple of months. These discussions continue on a monthly basis. And then we have another group that's organizing ongoing conversations about the laboratory operations software options. They're having a hybrid of conversations around individual presentations. And then in December, as you can see, they're going to be discussing a comparison among several of those options. And then you can see in some other sections that are planned early in January, including our quarterly membership orientation session, and an important session on publishing tips and activities to help you move your content to being closer for a technical paper and publication. ABRF's regional chapters are lining up their events for next year. Registration is not available just yet, but we wanted to give folks just a broad outline of the planned calendar for next year, kicking off with the ABRF annual meeting in March, and then proceeding with the schedule of regional chapter meetings all throughout the country, concentrating, as they usually do, in October. So, of course, as soon as those dates are finalized and registration opportunities are set, we'll be sharing that information with everyone. But just wanted to give you a chance to kind of mark your calendars or bookmark potential dates for those events. If you were a part of the ABRF annual meeting this year, back in March, or perhaps you weren't able to join us, a lot of the content has been captured, both the slides, recordings, summaries, and those are all available on the website at the link you can see on the screen. So lots of concurrent sessions, so you couldn't be in more than one place at a time. So this is a great way to access those resources. I hope you're participating in the ABRF core community, which is a great way to connect with the entire membership with a message, or there are over 125 specialty communities where if you have a particular question, perhaps it's on AI and bioimaging or another topic, you can reach out to your colleagues and ask for their help or resources, guidelines, metrics that they've used to answer those types of questions. So feel free to jump in. And if you have questions, again, reach out. Another reminder, registration is open for the ABRF annual meeting. The best rates are available through the end of the year, including the opportunity to participate in a special session you're going to hear more about continuing this process and these conversations shortly. But again, those best rates will be available through the end of December. And with that, I will stop the share and turn it over to Rich to introduce today's session.
All right, thanks, Ken. And just a couple of kind of program announcement. So due to the popularity of the AI and bioimaging workshop at last year's annual meeting, we're going to host it again. And we did learn some things from the first time. So one of the things that we're going to require for people who register, and it's part of the registration process for the meeting, there's like a check box there, is that you're going to have watched the 2 sessions on image processing, this session and the previous one, which are recorded and are available on the ABRF website. This one will be available in a little bit. Obviously, we haven't recorded it yet, but those will be prerequisites or requirements. And once you're registered, we'll send you some more information about what is required for the computer and software and what you have to download and all of that to make the session run a little bit smoother and a little bit more efficient. So with that said, again, I just want to reiterate what Ken said, is that basically any questions you have, please put them in the chat and we're going to answer them at the end rather than try to do it in between. And without any further ado, guys, take it away.
All right, I'm going to share my screen here. Somebody give me a thumbs up if you can see it. Okay, great. All right, moving here. Oops. All right, my name is Ben Abrams. I'm from the University of California at Santa Cruz, and I'm joined here by Dina and David. And as you can see from our title here, the general focus of today's lecture is going to be image processing. Okay, so the foundation that we laid down last time was really about understanding what a digital image is and its properties. Before we dived into those details, we did spend a little bit of time talking and sharing our thoughts on planning imaging assays. And we talked about a paper in particular from Ting-Lian Chu's group at Genelia, and thought that was a really good resource for that. But then we spent the rest of the time going over things like bit depth and dimensions of your images. We talked about linear and nonlinear image display adjustments. We talked about resolution and some of the limiting factors in resolution. Talked about things like signal to noise, metadata, ways and things to look out for in your images in terms of like aberrations and other artifacts. We also try to emphasize that when we're doing these and performing these image analysis workflows, it's often a really iterative process. And that is going to be a theme that's going to come up in today's discussion as well. All right, so today's session is going to focus on image processing, and we're going to talk about, start off talking about why we process images. Why would you even want to do this additional step? What are the benefits from it? And we're going to talk about how these processing steps fit into the overall image analysis workflows. Then we're going to dive into the details, some of the details about how some of these mechanisms work, these processing mechanisms work, both filtering and other processing operations. We're going to give some examples of linear and non-linear methods. Okay, so why process your images? What's the deal? So if you look at processing in the general image analysis workflow, or even before you introduce processing, we're always going to want to start with copying the data set, because you never want to work with your raw data, because if something happens to it, or if you apply some sort of correction or something that you can't undo, then you're really out of luck. So we always want to work with a copied data set, and then we're going to create some sort of binary image from that data set. And this is frequently, but not always, done through thresholding. And then we use these thresholded images to identify boundaries on our original data that we're going to use to identify the objects that we want to measure and hopefully extract quantitative data from. And that whole process is segmentation. We hopefully will have enough measurements and enough robust measurements to perform good statistics on them. So what does that actually look like in an image? Starting off here again with our copied image, and then showing the binary image, and then showing what we would do, how that would be reflected onto our original image to generate our segmented image that we're going to then take our actual measurements from. So again, this is the process of segmentation, which is generally just defining the regions of your image that you want to measure. And one of the key reasons that we like to process, or that we perform processing steps, is to enhance this process of segmentation and make it more accurate and easier to perform more reproducibly. It's also really helpful in helping to reliably produce quantitative data. Okay, like many of the other steps in image analysis workflows on the acquisition side, segmentation is also an iterative process. When you have your image and you go to make that binary, the first way that you try to do it might not work out the way that you intended, or you might not be getting all of the objects segmented in the way that you anticipate, or the way that you think would be helpful for your analysis. So you might go back and forth between the binary image and the original image, or the binary image and the segmented image, to bring in or filter out different objects that you care about. Okay. So when you're doing this, a lot of people, when they first start off, are trying to do this with manual segmentation. And this is just showing a window in Fiji. That is one way to do this, where you go image, adjust, and then you try to set your thresholds by sliding these sliders back and forth to draw regions around the areas that you actually care about. And the thing is that this is kind of a harder to reproduce a method of creating your binary, because you can generate multiple images that may look the same by eye, but may have subtle differences. So as I go to the next slide, you're going to see the image on the left, the bottom left, looks very similar to the one before it, but the actual size of those images are actually going to be a little bit different than what you're seeing now. And it can be as you go back and forth, depending on how you set your gates, it can make a difference. Now, this is a really simple object, really simple image, so maybe the image is not that great, or maybe the difference is not that huge. But if you're segmenting a lot of objects, and maybe the overall size of those objects is not small, making these subtle changes can make a pretty big difference in your overall outcome and the answer that you might get. All right, so when we can, we like to implement automated methods, because they're easier to implement evenly across a wider range of images. It can be less labor intensive to implement these automated methods, and this is just an example of an automated method, again, performed in Fiji, using the auto threshold function and choosing the max entropy option. So a lot of times, again, if you want to apply an automated method across multiple images, processing can be required to get them all to conform to a way that the auto thresholding algorithm can recognize and produce a good, clean result. So then if we go back to our workflow, we can see that the initial processing and filtering steps may fit into this part of the workflow up here, as you're going from that initial copied image and creating your binary. I also do want to point out that there are other ways that we talk about filtering in image analysis workflows. So the ones that I just mentioned more is a step of applying a kernel, or like a kernel-based filter. We'll talk about kernel-based filters in much greater detail later on when I hand over to David and Dina. But we also talk about filtering, like once we have generated that binary image, we may filter out different objects within that binary that we don't think describe or capture part of the image that we actually want. There's also filtering later on once we actually get our quantitative metrics, if you have some values that are way outside two normal distributions or something like that, then we might choose to filter out outliers or things that we think are erroneous for some other reason. All right, so again, the processing and filter steps are usually done on the original image, but some are also done on the binary. All right, so in this particular image that I started off with, going from the binary to the end segmented image, it only required very little intervention because this was a pretty good image to start off with. In this case, I was just using, in this example, using the analyze particles function in Fiji, and redirected, set measurements to redirect to the original image. And in this case, all I really had to do to get the objects that I wanted to was apply a circularity filter that's part of the analyze particles workflow, and just to filter out this small red dot here that's in the lower left-hand side of the binary image. It's not as easily visible in the original image, but it's not something that we were interested in. So that's an example of an object filtering step that you might have used. And so this brings up an important point, and that is if your image is good to begin with, you might not necessarily need to filter or process it. If you start off with something great, you can just go with that, and that's great. That's great. That's I think that what all of us are striving for. I think all of us who are directing chords would like to enable everyone to do. Although sometimes it's not really possible. So what I'm showing you here on the left, just the original image, and then on the right, for those who are not familiar, this is just what comes up when you go to in Fiji. If you go to image adjust, and use the auto thresholding algorithms, and you can do the trial option. It'll give you a number of different options to try to create that binary image. And the thing is that often, real images have flaws, and this is how this image actually started out. This image is just of rice grains, but you can see for a number of the auto thresholding algorithms, they tend to drop or miss objects that are in the bottom part of this image. You can see this in these examples up on the top row and a few on the next row down. You can also see that the higher background uneven illumination in this image really was troublesome and problematic for some of these algorithms, like these couple here in the middle and the one on the bottom here, where you're not going to get clean segmentation of the objects without doing some filtering or processing first. So in reality, this image that I showed you was really only good after processing. And this one, we just used this subtract background functionality in Fiji. You can read more about that if you look up this reference down here. But that was the reality. This took a little bit of processing to get to an image that was segmentable or thresholdable in a really clean way, producing these nice clean binaries that we were after. So processing can also be used to isolate other features in your target that or target features in your image that are obscured by other irregularities. In this case, this was some spinning disk data, looking at some cells, and you can see just in the way that this image was captured, there's this kind of striping pattern just because the spinning disk was maybe not operating at an optimal frame rate in this particular image. You can also see there is some maybe some misalignment or some uneven illumination. I think this is a transmitted light image, so maybe the field diaphragm wasn't adjusted properly. But anyway, there are these artifacts and undesirable things in this image. And in this case, a processing step using the image calculator was used to produce the image on the far right here that doesn't have those patterns and is free of the dark corners and other things that make that image a little bit more problematic to perform analysis on. Another reason that you may want to try to process your images is the reality is that sometimes when you're acquiring data, the acquisition conditions, like the sample conditions, don't allow you to take an image that's as clean as you'd like. This is 2-photon data, intracranial, intravitreal imaging, looking in a pretty deep into a mouse brain, and the object here, the subject needed to be recorded pretty quickly to minimize the impact on the animal. And if someone was trying to count the cell bodies in this particular field of view without processing, you'd have a hard time doing it with any of these different auto thresholding algorithms shown on the right. However, if you were to go and do a median filtering step on that image, you can see that enables a lot of the thresholding, auto thresholding algorithms to perform much more robustly, where you could more cleanly identify, cell bodies and other, other artifacts or other objects that you might be interested in that particular image. And so again, the goal here is to make the image more segmentable, not necessarily pretty. It does have the secondary effect often of making the image more pretty. But I do want to emphasize that, when you're performing these segmentation steps, you're really doing that to make a nice binary that you can then reflect on your original data to take your measurements. And I also want to take a second here just to say that the segmentation is not the real subject of this lecture today. We're going to have our own devoted session about segmentation that's going to be led by Erica Wee, and that's going to be in January. But we also felt that it was impossible to really talk about image processing in a realistic way without talking about segmentation, because it's such a critical step in image analysis workflows. But stay tuned for that exciting session in January. Okay, so what we're going to spend a lot of the rest of the time talking about is how can we understand what is actually happening at the pixel level in these processing steps. What other methods may be used than the handful that I've shown you here, and what are the implications for using them? Why would you want to use one? Why would you use another? And how does it affect the data that may be coming out of your image or may be able to be extracted from your image? So with that, I'm going to stop sharing here, and David is going to take over. Okay, I should have stopped sharing there. Okay.
Can you hear us?
Yes.
Cool. So I will now take the deeper dive, and that you have get a better, deeper understanding what happens on the pixel level when you filter an image. I tried to sort this out to make this in classes in the way of, now we have a spatial filtering with kernels in space, and we have a frequency filtering where we do this in the frequency space. So first, I will concentrate on this spatial filtering and try to mention if this is a linear or a non-linear filter on your problem. Again, this is only to make our life better and we get less biased and picking features for our segmentation. So we want more robust. So I first want to explain you what are the key features for spatial filtering. So the first key feature, what people get bombarded with, is what's your kernel size? The kernel size is a small little part of a kernel that is then moved over the image with altering the numbers from the image. So when you think of a kernel size by 3, this is exactly what happens. You take a 3 by 3 kernel, get this over the image, and generate a new image with this kernel. Now the question is, what function or mask is in the 3 by 3 kernel? This can be any number what you can think about, that you say, okay, take any number in this kernel, multiply this, divide this, or compare this to the edges. This is just the example that a kernel on this case will do this, a 3x3 kernel will do this for all 3 images and will replace the center pixel in the 3x3 kernel by the value 14. This is an example that math is behind this. We're going in the nitty-gritty in this. So a graphic representation of this problem would be this. On the left-hand side, you see the original. On the right-hand side, you see what you get when you have a 3x3 kernel and the middle one is a 1. So nothing is changing in this. So you get the same image. When you the center pixel and you don't count the surrounding pixel and you have this, you dim the image by half. When you will just use for the center pixel, you do the right pixel, you will move the image to the left. So when you do this 1 time, you see nothing. But when you do this 10 times, you would see that the whole image is shifted to the left. He didn't add black, he added the last pixel value in there. You see there's stripes on the right. But now we can implement, now we go to the nitty-gritties where people say, okay, I don't have a 3x3 kernel, I have a 3x3, but I only look at the whole thing, or only the edges, or only the, what is called, the centers. So don't be confused. Sometimes you even get this question additional where they ask you the kernel size and how to treat the edges and not. As a reminder, these kernels are changing the pixel values dramatically. For example, this is a line where the original has a 10 and there's a sharp edge. When you run a smoothing filter over this, you will smear out these edges and the intensities will leak out into the neighboring pixels, because this is what these kernel filters will do. They will interact locally with the pixel that are in the kernel size. One kernel that's often used in the special filtering is a Gaussian kernel. Normally, nobody will use a 30x13 kernel. I'm just making it so big that you believe that this is a Gaussian in there, because when I would show you the 3x3, I can show you any number and you say, I don't know if this is a Gauss or something else. But a Gaussian kernel, you can do this. So the question is why you would use a Gaussian kernel on your image. The answer is it will make your resolution bad. So when you have better optics, you get sharper structures. When you use a Gaussian kernel, it will exactly do this with your image when you have an optic that's worse compared to before. The question is, why you want to destroy your resolution with a filter? The idea on this comes from the signal to noise, because remember from the first session we did this, the noise is the jiggering around the signal. That means when I do this now on my image, and I have an example here, that's the rise image, and I apply a Gaussian kernel and with a 3x3, this is the picture on the right-hand side, I get a smoothed version of this, like that I have a worse microscope. But when I look at the profiles of these things, I see that on the left-hand side, I see a lot of the noise. This is the jiggering around the base level and the jiggering stuff. And on the right-hand side, on the Gaussian version, there is no noise. So when you have problems in images with noise, or you want an easier segmentation for the threshold methods, this helps a lot. And especially when you don't care much about the size because you have big objects like DAPI. A lot of the times the DAPI is bumpy and it's noisy because you don't care so much. This helps a lot to making your DAPI detection way easier. This is a linear filter, meaning you can even trust the values in there before and after, meaning when you compare control and experiment, the same delta is there in intensities, and very important, sometimes it's even sub-pixel position precise, meaning nothing will change the position. So when you care about detecting distance from one object to the other object, this filter will keep the position in place, even sub-pixel resolution. Another filter people often use, most likely in tracking, is the difference of Gaussians, DOGs. What this will do is, it's what the name is, you take a Gaussian filter with a small filter, you take a Gaussian filter with a big filter, and you did what Ben talked at the beginning, you just subtract this image from each other. So what you get is the difference of Gaussians, and what you get is the right image. The nice feature of the right image is when you choose the filter size of the objects you want to track or you want to keep in the image, what you can see at the profiles is it's causing dips around these objects. So when you have a very simple method for finding maxima, this helps for detecting and tracking spots, because these maxima are literally tracked of darkness around them. And because of the size, you can define the size of what you want to keep in the image. So this is because there are two Gaussians linear, because it's two Gaussian, it gets the position right, and this is for this reason often used in tracking. You see this a lot when you get filtered image, when you get tracking, something like, you want to do a DOG filter on this? And you say, yes, that's a good idea. Another filter often used in fluorescence is a median filter. The reason for this is, you can see this on this example, is oftentimes our fluorescent intensities in the histograms are skewed to the right. And when you then apply a median filter, what you do is you lift this median values in there higher than the noise, than where the bulk of the background level is, and that leads to the fact that you bump the intensities of fluorescence, and it will make your thresholding easier. So this is an example of a galaxy. I median filtered this 3 by 3. I just want to mention this to you, that you see and understand this once, is when you look at the big star in the center and the little star down to the left, this in there, and now I make a profile on this and I compare the profiles from the original and the median filter one, you see that the relation of intensities are totally switched between the stars. So that means you can use this easy for thresholding and making your thresholding easier, but any measurement on this is most likely false, because the positions are shifted, the intensities are screwed, and don't do this on the filtered image. But you can use this easy for making your thresholding easier, and to measure this in the original data. Another thing where we use filtering, for example, is something where the intensity by default is not good for the thresholding. In this case, this is a phase contrast image. Phase contrast works with phase interference. There's positive, then you are white, and then there's negative, then you are black. So the stuff where you have black and white, this is where the cells are. The stuff where gray is, this is where your background is. So when you will threshold this to the left, these are the dark pixels. You don't see where the cells are. When you threshold this to the right, with the bright pixels, this is not where the cells are either. So to overcome this, often people use filtering like a variance filter. This is just an example on a 2D example. Let's say the blue is my signal, and on the left it's flat, on the right it's flat, and in the center you see the change from black to white. Now when you run a variance filter with a kernel size of 5 over this, you will see that this gives you exactly where you have a high variance. Variance is the delta from the mean from the background in there, where you have a huge amount of changes. And this is exactly what we will do on the image. So we will take the image, we will run a 30 by 13 variance filter, and suddenly my background, where there's low changes, goes black, and where my cells are, it turns into be white. And then the white is easy to threshold with an automatic method. And this is how you will get in the easiest way leading edge of wound healing. Because it's one filter and it turns out like this, really like black and white. This is a nonlinear filter, but it's very efficient to detect local changes in space, in X and Y, but it's very even powerful when you do this over the Z dimension. So when you have little small fluctuation of calcium and whatsoever, when you apply a variant filter over Z, it pops out like black and white. Another example would be a nonlinear filter like an edge detector. Technically, these are two filters smoothed together. That's the reason of these two kernels down there. But what you will get is out of the rise image exactly where the edges are. So when you are interested in what is the edges, what is the parameter of this would be a helpful filter for this. What you will see is it's not dealing with the noise. The noise is still the same, how bad this is, but you will get exactly where the edges are in the middle of this is cut it out. The other part of filtering is happening in the frequency domain. And this is a very powerful tool because it has some advantages or disadvantages compared to the spatial stuff. The one disadvantage is it's way less intuitive because of something like, what? Okay. But hopefully I can convince you that this is not so hard. So when you take a signal that's the red thing and you calculate an FFT of this, what you will see are the frequencies of the function that's in there. So I have 5 cosine functions in the upper term, and when I want to know what frequencies they are, I do an FFT. That's an easy example of a 1 dimension. When I do this in 2 dimension, like an image, this would be the frequency space now is split in X and Y. You will see how these pixels in the frequency space would line up with a certain feature in the image. So when you have smaller lines that are the frequency is big, you are more to the center. And when you increase the frequency faster up and down, you are moving to the outside. And depending on where you are at X and Y, you change the direction of the frequencies. So the smaller lines with the most frequency, the fast frequencies are down to the right. And when you change the orientation or you change the frequencies, when you change the orientation, you will move around. When you change frequencies, we go from in to out. So when I do on the up left my image and calculate the FFT, I would get a gray image of this, where I see a little bit of more gray in the center. This is the resolution limit of light, and then I can calculate this back. So this is boring, but you get the concept. So the concept is I can calculate out of an image an FFT and move this back to the image. But now I can play with this. What people often do is they say, I did a high pass or a low pass filter on this. What they mean is with the low pass filter, you only let pass the low frequencies in the new image. So what you get, the low frequencies are the big structures. With the high pass filter, you do the opposite. You only let pass the high frequencies and the small structure stays in the image. In the case of the example from us before, when I have my image and my frequency space, and I will take only the white part from the frequency space. So I will ignore the dark round thing in the middle. So I cut out the low frequencies. I will come from the original image to a high pass filtered image. When I do the opposite, when I only concentrated on a low pass filter, meaning I get only the low frequencies, this is now the white part of the image again from the frequency space, and I will ignore the black part, I get the big structures. So, again, this is always that we get a more robust feature and that our thresholding will work better. When I do now a thresholding on the high pass filter, the original and the low pass filter, you will see that I will get different structures from my segmentation. And for example, the fine structures of these things on the high pass filter, I can't get with the original, even when I choose a different method for thresholding, because they will even fuse together. And on the other side, when I'm just want count big cells in there, that's an easy way to get a low pass filter to say, okay, I'm not interested in the small tiny things. I just want to see how many big blobs I have there. Because this is in the frequency space, and the frequency is laid out with the frequency and the orientation, it's the easiest is to cut out frequencies that are in the image. In this case, I have a frequency of horizontal lines. When I just cut out the horizontal dimension in this, I get rid of the lines. Or the opposite, when I have lines in my image, for example, from a muscle Z-bands, they will pop out in the Fourier space immediately like points, because they say, oh no, there are distinct frequencies in the image that appear all over again. And now Dina takes.
Okay, everyone. So at this point, we've talked about filtering your data, right? And the different types of kernels out there, the different types of filters and what they do to the data, and some examples of some of the filters you might want to use to clean up your image to get better thresholding and segmentation. At the end of this process, you get something called the binary. Now, this is a term we've been tossing around, right? But this is the process, right? An original one, I filter it, I threshold it, I hit apply threshold, and I get this black and white image. So what is this binary that we've been discussing? This is what actually identifies to the computer the structures you want to count. So now I can take this image and I can say, I want you to count everything that's going to be in the white areas or everything that's going to be in the black areas, right? We also sometimes call this a mask. So you'll hear that term tossed around sometimes. And it's a really powerful tool because now once you've gotten this binary, you can manipulate it to really fine tune what it is you want to count. Now, what are the kinds of things you want to manipulate? So here's an example, very simple. 2 nuclei, right, that had fused together or were in the process of splitting. Now, if I only did this on an intensity basis, I would see just one object, when clearly everybody here is like, no, that's 2 cells, count that as 2. There's a binary operation called a watershed, which will then segment things that are fused together into distinct objects. So this is a really popular, powerful binary tool. I don't want to get into the math of how it works, but we're happy to talk about that after the fact if you're interested. Okay, another example of this is skeletonization. So here you've got this nerve cell. If I actually wanted to trace how long these filaments are and how many branching points there are, I can do something called skeletonization. So now it collapses the wide objects into a single track, and I can measure linear distances and branching points off the skeletonized object, which I wouldn't necessarily be able to do in this case. Right? So another operation. One of the more popular ones is eroding and dilation. So if I have my original binary over here in purple and I erode it, I'm essentially saying to the software, take a pixel off the edge of my structure. And I have defined where the edge of the structure is when I made it a binary. So when the values go from 0 to 255 or from black to white, that's the edge. Shrink that, right? And it goes down. Dilation is the opposite. There's the edge, make it bigger. So if I've got a nucleus and I take the binary and I erode it, I start shrinking that down a little. Whereas if I dilate it, I start blowing it up. All right? Okay. I can now take these binaries and I can apply Boolean operators to them, right? To create new filters, new masks, new binary layers. So many of you guys have seen these before. I think almost everybody in the audience uses these terms in searches all the time. So I've got mask A and mask B, and if I do an AND function, I'm looking at the stuff in the middle, right? Give me where there's A and B. A or B will give me everything, give me anything that has a dog and a cat is only dogs and cats together. Give me anything that has a cat or a dog is going to give me all the images with cats and dogs. All right. A, not B, is give me all the images that have cats, but take anything out that also has a dog in it. XOR is give me anything that has cats or dogs, but not both, right? So these are really common terms. You can use them in your images. So remember, we just did this. We eroded one, we dilated the other. I can then use a Boolean operator to create a ring, right? Where would I want to do this? Why would I want to do this? Well, if I want to look at things that are happening at the nuclear membrane, right? What's happening exactly at the membrane? Is it on the membrane? Is it inside of it? Is it outside of it? I can now create this really nice string on the edge of my nuclei. All right. And that's an XOR function. Okay. How else can Boolean operators be applied, right? You can also do this on two different masks. So these are helicels. I have nuclei and I have lysosomes or puncta in my red channel. And what I want to say is segment my nuclei, segment my puncta, and then please just give me the puncta that are in the nuclei. I don't care how many are in the cytoplasm. I'm just counting what's in the nucleus itself. So Ben actually wrote a really nice macro and automated this, but it's great. You're going to see Fiji running through it. And now that's all it's doing is it's taking those two masks and looking at what's overlapping in the middle of it. And you can see here, we've got puncta right here. You can quantify their area and their mean intensity fluorescence. And you can do this very, very automatedly, right? Whereas before, if I was trying to do this manually, you'd be here for hours trying to really tightly draw a circle over those or erasing stuff that was outside of the nucleus, right? So extremely powerful in your analysis. Okay. So that's what happens when you apply Boolean operators to your binary objects, right? But when you're looking at the binary itself, you might want to do some other types of filtering, right? So I've got my original image, I thresholded, I have this binary. If I wanted to quantify something like average area, I'm going to have a problem because it's going to count these little guys on the edge as small objects, and it's overall going to bring my average down artificially so, right? So I might want to do some other types of filtering on this binary to exclude things on my edges, right? There are lots of different things you can do on this level. I just pulled this out of Fiji. Here are some of the filters, right? So we talked about excluding on edges. We can also say fill in these holes, right? So I excluded the edges, I filled in the holes. I can also do filters such as, hey, give me a size filter, give me only the small things or only the bed things, or give me only the round things or the spindly things. Anything that's long is bacterial contamination, just give me the nuclei, right? So there are ways to clean up your imperfect binary without it confounding your data. Okay, so that's binary object filtering, right? And that's where we are. The other thing I want to point out is once you get your binary and your mask and you want to do your measurement, you do that back on your original, right? Because if I was just going to hit measure here, all I'm getting is black and white values. I'm not getting any intensity. So I apply them back to my original image. And I've got, in this case, area mean, max, and min values. But there are a lot more options than just area and mean, right? And I'm just going to give you some examples of these. We're just going to touch upon them. There's a million more than what I've got in here. Okay, so once again, this is from Fiji. If I can go ahead and click on any of these buttons, and if you go to there's a Wikipedia essentially for Fiji, it will tell you the definitions and give you examples of all of these, and that's where some of these have been taken. So some of the gray value options, right? If I have an image, and I really simplified this, where I've got these intensity values in my 7-pixel binary little mask, if I take the mean, I'm going to get a value of 120. If I take the mode, I'm going to get 50. If I take the median, I'm going to get 90. My max value is going to be 300. My min value is going to be 50. My integrated density is going to be the area times the mean value, right? So if I've got two different objects, one's 4 times as big, if I just do mean intensity and they're both 120, I can't really see that. Whereas if I do integrated density, I'll see the difference between those two in that value. So what you pick is really dependent on what you're trying to analyze and what you're trying to see. So sometimes what you're going to do is you're going to use your binary mask and you're going to look at your different conditions and think about what you're trying to describe. Okay. Centroid versus center of mass. If I'm trying to find the middle of something, there are different ways of doing this, right? So there's a center, but I can also have that shift based on the intensity, and that's where center of mass is. All right, now, if you want to go into simple shape descriptors, right? I have my cells and they've gone from round to a little bit spindly. How do I address that? There are things like bounding rectangles, an ellipse, and a ferret's diameter. So the rectangle will just draw a box around it and give you that measurement. The ellipse tries to fit an ellipse in the center of that cell. So you get the maximum of that. And the ferret's diameter is the longest line across the center of the cell. So if I've got something that's gone from a circle to an oval, that diameter is drastically going to change. Okay. You can use these measurements to more accurately describe shape, and there's shape analysis. So they can be applied to quantify changes in morphology. So there's different types of area measurements. You've got your original, you've got your net area. If you fill the hole, it looks like the one in the middle. If you do a convex area, it's just essentially minimizing the dips in your structure. All right. Each of them is a completely different number in your readout. Perimeter, right? The edge of it. If you don't fill in those holes, you're going to get perimeter measurements for everything inside that lung tube, right? Okay. Major and minor axes. These are the longest lines you can draw in through a cell, and then the line perpendicular to it, right? So you draw the longest one you can, and then you go perpendicular and you draw the longest line you can in the other dimension, right? So on your major axes. All right. Now, if I take the min and max, the major and minor axes, and I put them on a ratio or put one over the other, I get the aspect ratio of a cell. Right? And you can see here, I've got 3 different cells across the top. And as they are, as we're going down, they're getting longer. So I can see that the aspect ratio isn't changing at all, even though this is getting roughly. But as it's getting longer, I can see that change very drastically in the aspect ratio. Conversely, if I look at circularity or roundness, I'm looking at the area over the major axis. And now when I look at these values, I can see how they're changing across, right? So there's lots of different measurements you can choose from. It is not just minimum, maximum, mean intensity, area. Once you get your measurements, you have to apply your statistics. Statistics are beyond the scope of this discussion. It's an entirely different thing. There actually is going to be a session at the ABRF meeting about statistics in imaging data. So we're going to have core directors on that panel who talk about how you run stats on imaging data. So that's a plug for the following meeting. Okay, so just to summarize what we talked about today, I want to go from the original to some sort of measurement. These are some of the steps that are very typical in an imaging analysis workflow. We have the original, we have to filter it or process it in some way so we can properly threshold and create a binary. Once we've gotten our binary, we choose what measurements we want to throw out, whether they be long or small or things on the edge. We go back once we get this mask and measure on the original image. We get the measurements we care about, and then we can see things over time and we run our stats. So that is the gist of our lecture. I'm going to exit out of this and stop sharing my screen. So you guys can go ahead and ask any questions you want.
Okay, are there any questions? You can either just raise your hand or put it in the chat, whatever you would like to do. And I just want to emphasize, something that David said is I use FFT quite a bit, especially like on sim data and stuff or spinning disk where you get these aberrations that are very constant. It's actually very, very easy to remove them using an FFT and then a reverse FFT. But I know a lot of people are really afraid of working in frequency domain. It's really not that complicated. David's laughing. Maybe it's just because I've been doing it for 40 years. I don't know.
I agree that it's not complicated, but you have to know what it's doing. So I
Yes.
think that's really what's key about the point we're driving home is like, it's easy to do these things, but you have to know what the button does so you really can harness the power of these filters in your images.
And please don't just click through filters until you find something that you think works. You have to understand the math behind it and be able to defend it. I get this a lot when I review papers. It's like, well, I just did this filter. And it's like, I ask them, well, why did you choose that filter? Oh, it made the image look better. Yeah, you don't want to do that. All right, questions.
I had a question, but I couldn't figure out how to raise my hand.
That's totally fine. Go ahead.
So I'm curious about, as core directors, core managers dealing with users, particularly people who have no experience with fluorescence microscopy and imaging and analysis. How do you approach teaching them, getting up to speed with doing the analysis and making sure that they're up to speed so they can acquire images correctly for their analysis?
So I can comment on that. I think we're unique in how we handle it, and I can tell you how we got here too. So you'll notice both David and I are in the same box, and that's because we're both at Northwestern.
Mhm.
We actually do a couple things. We have a Fiji and a cell profiler class that we teach. We alternate. It's a 4 or 5 day class. It runs 2 hours a day, once a month. Used to be free. We make users pay for it. $10 a day because otherwise they were signing up and not showing up and then re-signing up, right? It was just a mess, and that helped. And we're happy to share our slides and with you if you're interested in that. But the general workflow is once we want users, once they've been trained, we split training into 2 sessions. Actually, the whole workflow is we do a consultation.
Mhm.
We sit down. The first training session is with our training slide and not their samples, and we talk about just basics. The next session is supposed to be them coming in with literally like 2 samples, right? Your wild type and your knockdown, or your 48-hour time point on the edge of your morphological difference or your quantitative difference. And then like your single stain controls. I can tell you nobody does this, but this is what we want. And then we sit down on the scope with them and we let them futz around and we let them take pictures. And then they're supposed to meet with David with just like 3 images of each one. And can I run my analysis, right? David will actually come up with customized workflows, and then he sits down and trains them on the workflow. Like, hey, you want to quantify nuclei. So this is what you're going to do based off your image. You're going to run a rolling ball subtraction and then do this and then do that. And this is what each of them does. And then run off with your data, check them. I'm here if you need help. That's a lot, and we didn't start off that way, and that's a lot of effort, especially if you're at a small core. We initially started with a work study student who who was phenomenal, and then we wound up having her start training users on how to open up and deal with 3D visualization in Amiris. And then that grew into a justification for a full-time position. But that's a very long answer to your question, but that's
great.
how we handle image analysis here. I'm going to let Ben chime in because Ben's on the other end of the spectrum where he doesn't have a dedicated person who's just dealing with user analysis all day, every day. Or if David wants to comment on what I said.
Okay, I can first comment there. It's quite easy. The whole thing is an iterative process, and the earlier they start this, they get better images. So that's a common feature in here. When I move people to, for example, our Imaris station, the next time they will get better images because they see the flaws in the image, and that's the same with the analyzing. So when you say you can't analyze these images because you have saturation, don't trust the intensities, they never take saturation images anymore because they realize all these sessions they did for 2 hours is useless.
Yeah. Yeah, I'll chime in here a little bit because I have to say that I can only fantasize about having a David in my life right now as a single staffed core. So I do rely on the resources that I can find. You know, I'm a big proponent of telling people, hey, you know, read this paper before you, or as you're getting into your analysis, read this paper. I mean, one of my favorite resources is that paper on reverse workflow thinking that we presented in our first session. That's one of my favorite resources. I sometimes have bandwidth or the opportunity to lecture on imaging or give formal lectures on imaging, generally to like first-year graduate students, but I don't always get a chance to do that. And so, I do have a pretty good slide deck for when I've had those opportunities, and I do try to slip in and kind of step out of or incorporate those into my training sessions. My typical confocal training session tends to be about 4 hours long. We take a break in the middle, and I do, jump out of it and jump into, theory land to show them, resolution and things like that. And I found that a really fantastic and approachable text on this is actually this, I don't know if you can see it. This is the Fundamentals of Light Microscopy and Electronic Imaging by Doug Murphy and Michael Davidson. Our university provides access to this resource as a electronic resource so people can do it or access it. And I find that it's really approachable. It's really straightforward. It's starting to get a little bit, outdated in terms of some of the technologies, but the fundamentals are there and they're very solid. So finding, the best resources. And then as both Dina and David emphasized, I always try to say, yeah, this is an iterative process. Another thing that I really try to emphasize really strongly is that, it's really the wrong way to go to collect all your data, like, spend 3 months collecting all your data and then go, okay, now I'm going to start imaging it. That's not good. What you want to do is collect the minimal data set that gives you a reasonable estimation of the variance that you're going to see in your samples, and then take images of those initial samples and drive them to, data extraction. Take it all the way through your processing and analysis workflow to get to your end result on a small number of images, and then see, what you can do moving forward. See how you can expand it to more sample types. So, those are the things that I try to do, and then. I do offer to meet with people to help develop their analysis pipelines. Those are typically one-on-one sessions. I have a whiteboard in my office, but actually I more frequently now allow them to plug into my external monitor and show me what they're trying to do on their computer in my office in a digital way, because everything now is digital. And that's been actually super helpful. I just pivot the monitor on my screen, tell them to plug in. Then I work on their workflows. If it's 2D, I usually, recommend, trying Fiji. If they need to batch process a lot of stuff, our facility does have Amaris. So batch processing in Amaris is very nice. And then for more three-dimensional stuff, I almost always, suggest turning to a more, a really powerful tool like Amaris. So those are my basic tips.
So like Ben is we have 2 people now in the core until I leave, but I have found that running workshops, so I do at least 2 workshops a year. One of them is based on Fiji, and it's the most common needed routines. And then I do one, basically a much longer one on like basic imaging and some advanced imaging. And then, I also do one on optics and stuff like that. I have scaled back doing programming because I find that it is extremely difficult in a relatively short time to teach people Python or R or any of these and really have it efficient. So like Ben is I meet with the people, and usually if it's a complicated workflow, I develop the workflow for them using either Amaris or Image Pro, or if it's simple enough like Fiji, and then basically just turn them loose on that. But the one thing which I have found very helpful is determining the number of samples, what your N really needs to be. And like I think Ben mentioned, or maybe it was Dina, is collecting a few images so you know your variance, and then you could basically use the formulas to determine what your N has to be, right? Because what I find is people either collect way too many or way too few on their variance, and then they come to me and say, well, and I tell them it's all in the noise. You need a higher N, or you've wasted, and I'm not going to tell your PI this, but you've wasted thousands of dollars on a very simple binary question where you did not need 3,000 images. You could have done it with 30. And this is even more important as we move into AI and the training sets and that type of stuff. So I think that hopefully that answered your question. It was a long diatribe, but I think we got there.
Yeah, just to comment on what Rich said is the N comes out of what is the difference in measurements, and this defines as well then what instrument you need to use. Right, so when somebody comes and say, I don't know if so when you need 1 million images, yeah, a single pin or confocal is a no.
So any other questions? I see we've lost a few people here. Let me see, I don't see anything in the chat. Okay, if there's no other questions, I will give you the next 23 minutes back. All right, thanks, guys, and hopefully, we will see you at the next one. We're taking December off, so remember, it starts in January. And if you are registering for the meeting and you're going to do the workshop, remember, you have to watch this one and the previous one on image processing. All right, guys, thanks. Happy imaging.
Thank you, everyone.
Thanks, man.
Bye.